All right, so we had a question about Rolle's theorem, and I worked out this example, but unfortunately when I was recording, things crashed, and I wasn't going to re-record the entire video, so I will explain this problem before I answer the next question that was asked. So here we have the function f of x equals x squared minus sine pi x over 6 over negative 1, 0, closed interval. So the question is, we want to first check to see if Rolle's theorem can be applied, and if Rolle's theorem can be applied, find the value of c such that f prime of x equals 0 in the interior of that interval. So there's three requirements to Rolle's theorem. You have to be continuous on the closed interval. Now, how do we know this is continuous? This is continuous because that is a linear continuous function, and that is a trig function. We know it's continuous because both of the individual functions are continuous, and we have a property, a theorem in chapter 2 that says if you have two continuous functions and you add or subtract them, then you get a continuous function. So we know that's continuous. You know, there's no asymptotes anywhere, there's no holes, that kind of stuff. Now, so it's continuous everywhere, specifically over here, from negative 1 to 0. So on the closed interval, it has to be continuous. Now, we also need to check to make sure it's differentiable on the open interval. So how do you know it's differentiable? Well, here's how you know it's differentiable. You find the derivative, which I've already worked out here. Here's the derivative. You look at the domain of the derivative. If the domain of the derivative is defined on that open interval, then it's differentiable on that open interval. In fact, the derivative here is defined for all real numbers. So that means the original function is differentiable for all real numbers. So to figure out if a function is differentiable or not, simply look at the domain of the derivative. If there are any points where the derivative is not defined, then the function is not differentiable at those points. But here, the derivative is defined for all real numbers, so the function is differentiable for all real numbers. Specifically, it's differentiable from negative 1 to 0, excluding the endpoints. The third requirement for Rolle's theorem is that f of a equals f of b. That is, the y values above the two endpoints of your interval have to have the same height. So we have to verify that, and unfortunately I have erased that work. So I guess maybe I'll outline it really fast again. F of a, okay, the original function, that's, not f of a, f of negative 1 is f of a. F of negative 1 equals negative 1/2, since x is negative 1, minus sine of negative pi over 6. Now, negative pi over 6 is an angle right over here. And what is the y value of that? It's negative 1/2. So you have negative 1/2 minus a negative 1/2, and you get 0. So f of negative 1 is 0. We need to evaluate f of b, which b in this case is 0. So f of 0, well, you have 0 over 2 minus sine of 0. Well, 0 over 2 is simply 0, and sine of 0 is 0. So we do get f of a equals f of b, so we're good there. So now that we have checked those three requirements, we can know that Rolle's theorem is appropriate to use here. If we had not checked those three requirements, we would not be ready to use Rolle's theorem. We have to check those three requirements first, because if any one of those three requirements are not met, we cannot apply Rolle's theorem. Now, what does Rolle's theorem do? Rolle's theorem guarantees that somewhere in the interior of this interval, you have a critical value. And that critical value is going to be a maximum or a minimum. You're going to get an extreme value somewhere in the interior. So, as we saw in section 4.1, sometimes if all you require is that the function be continuous, then the extreme value might happen at either A or B. So the endpoint might have a maximum or a minimum. But if you want a max or a min in the interior, then Rolle's theorem is what you're looking for. So we are guaranteed somewhere in between negative 1 and 0 to have a horizontal tangent line a maximum or a minimum? Specifically, a max or a min. So let's see. We take the derivative, which is here. We set the derivative equal to 0 and solve. Now, this one is weird because we end up with this equation right here, which is cosine of something equals this, which is not something on our unit circle. Now, when it's something kind of crazy that's not on our unit circle, we need to take the inverse cosine, in this case, of both sides. So we take the arc cosine, which is inverse sine of both sides. The reason we do that is because when you take the function and compose it with its inverse, you simply get the argument back. And so now we can solve for x. So x equals 6 over pi times the arc cosine of 3 over pi. If you simply type that into your calculator, you get this answer approximately. But the problem with just that answer is that's not in the correct domain. We're looking for a critical value in -1 to 0. So if you think about it, I drew a little picture here. This is an angle in the first quadrant. That's radians. So, 1 radian is somewhere about right here. Let's see. If you have pi radians, that's 3 radians is pi. So, that's 3. So that's actually a little bit too tall. It should be a little lower. A little bit of a smaller angle, but that's just for reference. It's an angle in the first quadrant. But we know that cosine is positive in the first and the fourth quadrant. So there's an angle here with the same cosine value. So the angle here, we would usually do 2 pi minus this number, but that's not going to get us in the correct domain. So we do 0 minus this number to get us our critical value in the correct domain. So we are looking for this angle, which we call negative 0.5756. So that is the critical value we were looking for. Now, as far as Rolle's theorem is concerned, that's all we need. Rolle's theorem usually just asks for the value of x. Usually we say the c value. C is just a specific x value. The value of c where that horizontal tangent line occurs. So there's the x value, the c value. Now, usually I require my students on tests and such to give me x comma y. So if you want to find x comma y, here's the corresponding y value. How do you find the y value? You take that x value and substitute into your original function. So here's x comma y. But just to be clear, this is all the question asked for, was that value. Now I did go ahead and I was thinking to myself, again when I was recording this earlier, I was thinking to myself, is this a maximum or a minimum? Well, I don't know. I'm not sure really what the graph, I know what it kind of looks like, but I don't know the particulars of that graph. So I'm not sure if that's a max or a min, but I can figure out by using the first derivative test, which we learned about in section 4.3, or if we haven't gotten to 4.3 yet, then we will learn in section 4.3. The first derivative test says this: look on the left of this critical value and look to the right and see what the derivative is doing to the left and to the right. If the derivative is positive, then that means the function's increasing, and if the derivative is negative, that means the function's decreasing. So what I did here was I picked a number really close, but on the left side of my critical value. Negative 0.6 is to the left. Then I picked a number barely to the right, negative 0.5 is to the right of my critical value. And then I plugged those values into the derivative. I didn't really care what the number was, I just used my calculator. All I cared was the sign. When I plug in negative 0.6, I get plus when I plug into the derivative, and I get negative when I plug in negative 0.5 into the derivative. What that tells me is that I am increasing when I'm just to the left of my critical value, and I'm decreasing when I'm just to the right of my critical value. And what that tells me is this situation happens. This is what the first derivative test tells us, that if you're increasing, then you have a critical point, and then you're decreasing after that, that critical point is a relative maximum. So that's how I understood, that's how I ascertained the fact that this point is a relative maximum. Now, Rolle's theorem doesn't really give you a good way to tell if it's a relative max or min. This is the first derivative test that I'm applying at this point. So I wanted to explain this. That's all that work. Again, I'm sorry that I did have this all in real time being worked out, but the computer crashed, and so the video was lost, and I didn't have a really busy day today, so I didn't have time to work it out because I wanted to get to this other question. So I explained this to you guys, and then I have another question for you. So give me just a moment. I will erase. And then we have another pretty interesting problem to look at. So let's see. It has exponentials in it, so it'll be interesting for sure. So let's see. Let me pull this up. We have the function. Let's see here. This is in section 4.1, so this is about the extreme value theorem. We have f of x equals 5e to the x minus e to the 2x. And we are concerned over the interval from -1 to 2. Now, this is an extreme value question. It says find the absolute extrema of the function on the closed interval. So this was before we had Rolle's theorem, before we had the first derivative test and all that kind of stuff. So far, in section 4.1, all we knew about was finding the absolute extrema. That is, finding the highest point, the absolute max, and the lowest point, the absolute minimum. Now, the extreme value theorem is really simple. The extreme value theorem just says this: if the function is continuous on the closed interval, then you are guaranteed a maximum and a minimum on that interval. The only problem is a lot of times those maxes and mins occur at endpoints, which are pretty boring. Okay, so you're not guaranteed the max or the min will occur in the middle here somewhere, but you are guaranteed that a max and a min will occur as long as this function's continuous. So we do have to make sure the function's continuous before we can even apply the extreme value theorem. Now think about it. E to the x is a continuous function. 5 is a continuous function. So 5 times e to the x is a continuous function. E to the 2x, in fact, well, let's go further. 2x is a continuous linear function. E to the x is a continuous function. So the composition of e up to the x and 2x, that composition is a continuous function. And the difference of two continuous functions is continuous. That is what we talked about in chapter 2. You can take two continuous functions, you can add them, subtract them, multiply, divide them, compose them, and as long as in that process really your denominator never turns 0, which we don't even have here, the function is still going to be continuous. So this is a continuous function. It's continuous everywhere, but we're only cared about from -1 to +2, but it's continuous everywhere for all x values. So we can use the extreme value theorem, and the extreme value theorem says this: find a derivative, set the derivative equal to 0, and that'll give you your critical values. Once you have your critical values, evaluate the original function at your critical values and see what you get. But you also have to do the same thing with a and b, your endpoints of the interval. So evaluate the function at a and evaluate the function at b and see what those y values are, because that might give you a maximum value or a minimum or vice versa. So let's see. Let's first find the critical values. So that means we need to find the derivative function, f prime of x. Now, that's easy. You factor a 5 out and take the derivative of e to the x. Well, the derivative of e to the x is just e to the x. So the first term's derivative is just itself. Super easy. Now, the second one is a chain rule. So just off to the side here, we have the, the outside function is e to the x. The inside function is 2x. So the chain rule says you take the derivative of the outside function, which is just e to the x, it's its own derivative, But instead of writing e to the x, you evaluate it at the inside function. So it's 2x. But then the last part of the chain rule is that you evaluate, you multiply by the derivative of the inside function. So the derivative of 2x is just 2. So if I just put a 2 there, that is my derivative. Now, to find critical values, we simply need to set the derivative equal to 0 and solve for x. So f prime of x equals 0. We have 5 times e to the x minus 2e to the 2x equals 0. Now, I know I have a lot of students get to this point and just get stuck because we don't know what to do here. But think about what that says. Okay? E to the 2x is equal to, well, there's a couple different things it's equal to, I suppose, where if you're different versions of the same thing. But this is equal to ex times e to the x. Because remember my rules of exponents, if you have the same base and they're multiplied together, you can add the exponents. So you can write this as e to the x plus x is 2 to the x power. So think about this. You can write, that's actually e to the x times e to the x. So you can factor out an e to the x. So if we factor out e to the x, we're left with a 5 there minus 2e to the x equals 0. Now, why is that important? That's important because we can use the zero factor theorem now because we have two items multiplied together equals 0. You know that one or both of those must equal 0. So we can set them both individually equal to 0 and solve those two easier equations. So we know that either e to the x equals 0 or 5 minus 2e to the x equals 0. Now, think about that first one. That first one has a graph that looks like this. There's a horizontal asymptote at the origin. It has a y-intercept of 0, 1. And what do you think about that equaling 0? This is asking, where are the x-intercepts? It never crosses the x-axis. It's a positive function. So it doesn't have any solutions to this. No solutions. Because this thing is never equal to 0. Now this is going to have a solution. How do you solve that? Well, let's just go off to the side maybe. Well, we can do it here. We'll move over here in just a second. Alright, so we're going to subtract 2e to the x from both sides. So we're going to have 5 equals 2e to the x. Divide both sides by 2. So 5 halves equals e to the x. Now, whenever you have a situation like that, you want to take the natural log of both sides. So I'm kind of out of room here, so let me move up to the side. If you take the natural log of 5 over half is 2.5, so natural log of 2.5 equals the natural log of e to the x. Now that's just a number. Let's just leave it as is for the time being. But the right-hand side simplifies as x times the natural log of e. But what does that equal? That's just 1. So we get x times 1, otherwise known as x, equals the natural log of 2.5. So I only have one critical value. So x equals the natural log of 2.5 is my only critical value. So critical values are where extreme values have to occur, or endpoints, since we're working with the extreme value theorem. So what we need to do here is test these. So we have a critical point is natural log of 2.5. We need to figure out what f of natural log of 2.5 is. We then need to do the same thing for our endpoints. So -1 and 2. So we need to look at -1 and f of -1. And then 2 we need to look at f of 2. And we simply, at this point, pick the biggest y value and the lowest y value. That's going to be your absolute max and your absolute min. So let's see. If we plug this into f, what happens? Well, you have 5 times e natural log 2.5 minus e to 2 times natural log of 2.5. Okay, let's think about this. In fact, I'm going to give myself some more room here. I'll write that again in just a moment. Now think about this. E and natural log are inverse functions. So what this results in is 5 times 2.5. Okay. Thinking about this, we could rewrite that as natural log of 2.5 squared using the properties of logarithms. That is, we can say e to the 2 times natural log of 2.5 is equal to e natural log of 2.5 squared. Okay. So what we do here is we have 2.5 squared, and these two are inverse functions, so the result is simply minus 2.5 squared. Okay? So let's see what that is. Okay, that's 5 times 5 over 2 minus 5 over 2 squared. So that's what 5 times 5 over 2, that's 25 over 2 minus 25 over 4. Okay, well that's 50 over 4. So that's 25 over 4. So that's the y value that corresponds to this x value. So let me do a little erasing. If you need to, back up and watch that again. But this is 25 over 4. And now we need to do the exact same thing for our two endpoints. So we need to do, let's see, -1. So that's an x value. This is an x value. F of -1 is 5 times e to the -1 minus e to the -2 power. Now, we could say that's, sure, we could say that's, 5 over e minus 1 over e squared. I don't know what number that is, so we need to get an approximation from a calculator. Let's see. 5 divided by e, okay, minus 1 divided by e squared. Oh, that's not right. E squared. It's approximately 1.7. So let's see, 25 over 4 is 6.25. So far that's the maximum, and that's the minimum. We have one more possibility, the other endpoint b, so 2. What about x equals 2? Well, we need to evaluate f of 2. F of 2 is 5 times e squared minus e to the 4th. Okay, well, I don't know what that number is, but we need to check it out. 5 times e squared minus e to the 4th, that is negative, well, I'm rounding here, approximately negative 17.7. So now what do you think? What's the biggest y value and what's the smallest y value? Well, I think there's the smallest, because it's negative 17. So it's the absolute smallest value on that interval. The absolute maximum and the absolute minimum are either going to be at a critical value or at the end point when using the extreme value theorem. So it looks like the highest value is that 6.25. So that's the absolute max. Now here's what we say. Let's be clear with the lingo. So we say -17. Actually, let's be exact here. That's the exact minimum value. So 5e squared minus e to the fourth is the absolute minimum and occurs at the point, let's see, 2, comma, 5e squared minus e to the fourth. So that's x comma y. So the y value is the minimum value. It occurs at this specific point. Let's do the same thing for the maximum. 25 over 4 is the absolute maximum and occurs at the point, let's see, natural log of 2.5, comma, 25 over 4. So section 4.1 is kind of just an introduction to this stuff. After this section, we really don't talk a whole lot about absolute extrema. After this section, we really move into relative extrema, finding a relative max or a relative min. So a max or a min in that general neighborhood. But in section 4.1, we're concerned with what is the absolute highest y value of this function on this interval, and what is the absolute lowest y value on this interval with that function. Okay, like I said, we tend to only care about relative extrema after this section, but in here the extreme value theorem allows us to find, as long as the function's continuous on that interval, allows us to find the absolute highest y value and the absolute lowest y value. Be careful with what is required as far as your answers. Sometimes, like if I just said, tell me the maximum is 25 over 4. But usually homework, quiz, and test questions are going to say, give me the x comma y of the maximum point, or the x comma y of the minimum point. So just be careful. If the question was, like, what's the minimum is that. That's the lowest y value. But if the question is, where does that occur, as in what's the specific point, then you want x comma y. So just be careful with how you're asked to report your answers, and don't do all the work and then report your answer wrong and miss points. Okay? Hope this has helped. If you have any questions at all, always feel free to ask on Blackboard, and I'll be more than happy to help. Talk to you soon.